Hi, in this video we're going to go through some worked examples, evaluating the eigenvalue decomposition, and seeing how we can use that to simplify certain types of problems. Let's begin with a problem addressing the question of diagonalization, or the eigenvalue decomposition, and when it fails. Can we demonstrate why, for this particular matrix, shown here, an upper triangular matrix in this case, why it is impossible to find a non-singular x and a diagonal lambda such that the eigenvalue decomposition holds true. I recommend that you pause your video, try to work through this problem on your own, and then resume to follow along with the worked solution. Okay, in order to solve this kind of problem, what we really need to be able to demonstrate is that we can't find enough linearly independent eigenvectors. In this eigenvalue decomposition, the matrix X will hold the eigenvectors, and the matrix lambda would hold the eigenvalues. In order for it to work, we need to be able to find a full set of linearly independent eigenvectors, enough so that we have as many rows and columns for a non-singular x. This requires us to show that we can't find enough. This will only happen in the case where we have eigenvalues that have a greater than one multiplicity in the factorization, the so-called algebraic multiplicity, but a smaller geometric multiplicity, that is, dimension of the associated eigenspace. How do we get there? We get there by starting with the same eigenvalue problem, evaluating the characteristic polynomial determinant of lambda I minus a. The diagonal entries will be lambda minus the diagonal entries of a. The off diagonals will be the off diagonal entries negated. Here, because we have an upper triangular form that we're starting with, the determinant is just the product of those diagonal entries, already nicely factored. The characteristic polynomial is just lambda minus 2 cubed. The only way this expression can be equal to 0 is if lambda equals 2. So what we have here is a single eigenvalue, but one with an algebraic multiplicity, that is the number of times it appears in a factorization of this characteristic polynomial, of 3. Right. Once we've identified that we have eigenvalues, and the eigenvalues that have a greater than one algebraic multiplicity, we go on and look at the eigenvectors. Plug in our lambda equals 2 into our expression of lambda I minus a. In this case, we get zeros on the diagonal and the negative of the a entries on the off diagonal. And we want to find out the dimension of and a basis for the null space of this matrix. We apply our standard approach here. We are already in an upper triangular form with 2 pivots, so we convert this into a reduced row echelon form by scaling and eliminating upward, and then scaling to give us a reduced row echelon form for our matrix lambda I minus a. This matrix has a single free variable. We have a pivot in the second column, a pivot in the third column, so only the first position is a free The first column represents a free variable. A basis for this, of course, would be found by setting that equal to 1 and choosing the pivot entries from that column, 0 and 0. This last piece isn't actually necessary for the problem at hand, because as soon as we've identified the number of free variables, we're able to answer this question. The eigenspace of this single eigenvalue has a dimension of 1. The geometric multiplicity of this is 1. The algebraic multiplicity was 3. 1 less than 3. We cannot find 3 linearly independent eigenvectors. In fact, the only eigenvectors for this matrix are scalar multiples of this single eigenvector, single basis vector that we found for the 1 eigenvalue associated with this matrix. We definitely cannot construct a singular X. This is what we're looking for in the case of failure of diagonalization. Okay. For the next problem, let's go on to perform a diagonalization, eigenvalue decomposition, in the special case where we have a symmetric matrix. We have a symmetric matrix A. We would like to be able to find an orthogonal matrix Q and diagonal matrix lambda such that this decomposition is satisfied. A equals Q lambda Q transpose. Just as a reminder, this is the special case of the eigenvalue decomposition in the situation where we have an orthogonal matrix Q is the case where the inverse of the matrix is equal to its transpose. It happens when Q has orthonormal columns. Okay. So, can we find this? I recommend that you pause your video at this point, try to work through the solution on your own, and then return to look at the completed solution. All right, once again, we begin this problem with finding the eigenvalues, which comes down to finding the roots of the characteristic polynomial. The determinant of lambda I minus A. The diagonal will have terms lambda minus the diagonal elements of A. All of the off-diagonal elements will be the negative of the off-diagonal elements in A. We want to find this determinant. We can find this one fairly simply by expanding along either the second row or the second column. We see this has a single non-zero entry. What would we get by the cofactor expansion along here? We're starting at position 2, 1, and so this starts with the negative piece. Negative 0, don't worry about what the determinant is, plus lambda minus 4 multiplied by the determinant that we get. If we cross out those pieces, we're left with lambda minus 3, negative 1, lambda minus 3. And the last term would also have a 0 here. Right? Single non-zero term multiplied by a 2 by 2 determinant. This 2 by 2 determinant is lambda minus 3 cubed minus negative 1 squared. Lambda minus 3 squared minus negative 1 squared. Lambda minus 3 squared minus 1. We're partially factored out here. We already have a lambda minus 4, but we need to sort of see what we can do with this remaining piece. Expand and factor as we've seen before. Multiply out the lambda minus 3 cubed is lambda squared minus 6 lambda plus 9. Subtracting the 1 takes us to lambda squared minus 6 lambda plus 8. This, we're looking for a pair of numbers whose product is 8 and whose sum is -6. This is satisfied by -4 and -2. They add to get -6, they multiply to get 8. So the factorization of this quadratic is lambda minus 4 times lambda minus 2. The overall characteristic polynomial is lambda minus 4 squared multiplied by lambda minus 2. This will equal 0 when lambda equals 2 or when it equals 4. We have two eigenvalues. One has an algebraic multiplicity of 2. We have a squared out term here. And the other has an algebraic multiplicity of 1. We now move forward finding eigenvectors, bases for the eigenspaces associated with each of these two eigenvalues. Let's start with 2. Plug that into the expression lambda I minus a. 2 minus 3, 2 minus 2, 2 minus 3 gives us -1, -2, -1 on the diagonal. And the off-diagonal elements are just the negated off-diagonal elements of A. We want a basis for the null space of this. Carry through elimination. The last row is the identical to the first, so it becomes 0. We already have upper triangular form. Scale these to give us our reduced row echelon form. We already have a 0 in this position. And this reduced row echelon form can be used to find a basis. We have pivot in the first column, pivot in the second column. Our third position is free. We set the free variable equal to 1 and pull out the values for the pivot entries by negating the appropriate entries in this column. We get a -1 and a 0. This vector is a basis for the eigenspace associated with lambda equals 2. However, for the decomposition we want here, we need an orthonormal basis, not just a arbitrary basis. We need to divide this by its length. Its length is 1 squared plus 1 squared. Divide square root of that, so square root of 2. We divide this through by the square root of 2, and an orthonormal basis for this is -1 over root 2, 0, 1 over root 2. Note that because we only have a single vector, it's really only the normalization piece that matters. We then go on to our next piece, our next eigenvalue, our eigenvalue of lambda equals 4, and we have we plug this into our lambda I minus a. 4 minus 3, 4 minus 4, 4 minus 3 gives us 1, 0, 1 on the diagonal. Off diagonal terms, just the negative of the terms in A. And carry through elimination. Third row is scalar multiple of the first, so it becomes a set of zeros. Second row was already a row of zeros. In one step, we have a reduced row echelon form. One pivot. Remember that this eigenvalue, the eigenvalue of 4, had a geometric multiplicity of 2. We have, in this case, two free variables. X2 and X3 are both free variables, so we have an eigenspace of dimension 2 that matches the algebraic multiplicity of this eigenvalue, which it should because we had a symmetric matrix and everything has to work out well when we have symmetric matrices. We plug the first free variable as equal to 1 and pull out the pivots from that column. That gives us the single pivot. from that column, gives us a 0. Our second free variable, we set it equal to 1, the other one equal to 0. We pull out the pivot value from that column, negating it to give us a 1. And we have these two vectors. Once again, we need an orthonormal basis. We check for orthogonality. In this case, we actually got lucky. If we take the dot product of xn2 and xn1, we get 0 plus 0 plus 0. These are already orthogonal. That means we don't need to do any extra work. If they were not orthogonal, we would have had to take an extra step of constructing an orthogonal basis. However, well, one of them has a length of 1 and is thus already normal. The other one has a length of square root of 2. We need to normalize this in the same way, dividing this through by its length, and this gives us an orthonormal basis for this eigenvalue lambda equals 4. One of the vectors is 0, 1, 0, and the others is 1 over root 2, 0, 1 over root 2. Now that we've found orthonormal bases for both our eigenvalues, we're ready to put everything together. We started with our matrix A, we found our eigenvalues and our orthonormal eigenvectors. To construct the decomposition, we simply take these eigenvalues and plug them into the diagonal matrix, making sure that we repeat the eigenvalues that have a multiplicity of more than 1. The eigenvalue 2 had a multiplicity of 1. Eigenvalue 4 had a multiplicity, both algebraic and geometric, of 2. We need to repeat it in this diagonal matrix. We then construct Q using the eigenvectors that we have found, being sure to make sure that they match up appropriately. The way we've written this down has an eigenvalue of 4. That means we need to take one of the corresponding eigenvectors and put it in this position. We had put a 4 here. We put the next eigenvector for eigenvalue 4 in the next column, and our last was our eigenvalue of 2, so we put the corresponding eigenvector here. We can double check that the columns are all orthogonal. They should, because a symmetric matrix naturally gives eigenvectors for non-equal eigenvalues as being orthogonal. So we have our final answer. I should note that this is not the only way we could write this. Given this ordering, this sort of definition of our lambda, we could have exchanged these two columns, and that would have been perfectly valid. Right? All that matters, so we have two different eigenvectors for lambda equals 4. Their order doesn't matter as long as they match up with these. We also could have ordered lambda differently. I could have written, instead of defined lambda as, say, 2, 4, 4. And if we had done this, then our Q would have had to been constructed differently. It would have to start with the eigenvector for eigenvalue 2, and then the next two could take whichever order we want. And so there is some flexibility in how we write these. One common way of writing this down is to have the largest absolute value eigenvalues at the upper left and have them decrease in absolute value as we go down, and that's what I've chosen here. Okay, so in a final example, let's think about how we can use the eigenvalue decomposition. Here we are going to, given an eigenvalue decomposition, this is actually the decomposition that we just evaluated, some A equals Q lambda Q transpose, where lambda is given by this matrix and Q is given by this orthonormal matrix. Can we use these results to find a general expression for C equals A raised to the power of K, where K is any positive power, a positive whole number power? And can we find a matrix such that B squared equals A? Let's think about these two problems in the context of an eigenvalue decomposition. Recommend that you pause your video, try to work through this on your own, and then resume to follow along. Let's start with the first of these. We want to find a general expression for A equals A to the K, for C equals A to the K. The heart of solving this kind of problem is recognition of this relationship. Anytime we have an eigenvalue decomposition of some A equals X lambda X to the -1, this lets us write a power of the matrix as taking the powers of the eigenvalue matrix, the diagonal matrix, and multiplying it by the, on either side, by the appropriate matrix of eigenvectors, or its inverse. Here we have the special case for a symmetric matrix where we have an orthonormal eigenvector matrix, which simplifies it even more that we don't need an inverse. Recognizing this problem really is as simple as plugging in the matrices that we already have, Q, represented here, Q transpose, where we've just taken each column, 0, 1, 0, and made of the row, 0, 1, 0, 1 over root 2, 0, 1 over root 2, 1 over root 2, 0, 1 over root 2, negative 1 over root 2, 0, 1 over root 2, negative 1 over root 2, 0, 1 over root 2. And to take A to the lambda to the power of K, we simply take each of the diagonal elements of lambda and raise it to K. After writing this down, we go through and just do the matrix multiplication. In our first step, I'm going to first of all multiply these two together. Multiplying a diagonal matrix on the left by a matrix has the effect of scaling each row by the appropriate entry in the diagonal matrix. So this gives us 0, 4k, 0. Scale this row by 4 to the k, 4 to the k over root 2, 0, 4 to the k over root 2. Scale the third row by 2 to the k, negative 2 to the k over root 2, 0, 2 to the k root 2. Then carry on with the matrix multiplication using standard forms. First row multiplied by the first column, 0 plus 4 to the k over root 2 is 4 to the k over 2, minus 1 over root 2 times negative 2 to the k over root 2 is plus 2 to the k over 2. And so that's our first entry. The first row times the second column is 0 times 0 times 0, giving us a 0 here. Our third entry of the first row is 0 plus, again, 4k over 4 to the k over 2, and in this case minus 2 to the k over 2. For the middle row, we have 0 plus 0 plus 0, so 0. 1 times 4 to the k plus 0 is 4 to the k, and 0 plus 0 plus 0, another 0. For the last row looks almost exactly the same as the first row with a different of a sign here. So the forms are going to look almost the same. 4 to the k over 2 minus 2 to the k over 2, 0 plus 0 plus 0, and 4 to the k over 2 plus 2 to the k over 2. We note that this is a symmetric matrix, as it should be, given that we know that A started out as a symmetric matrix. General form for A to the k. This is one of the benefits, one of the nice things that we can do about an eigenvalue decomposition. We can write general forms for for any sort of power of a matrix, which can be very helpful in certain application classes. Okay, now what about the next piece? The next piece we asked, can we find a matrix B squared, a matrix B such that B squared equals A? This is an interesting one because it kind of hits at the idea of a square root of a matrix. If these were scalars, what would we do? We'd say, how do we find B squared equals A? We would say that A equals plus or minus the square root of B, right? And if this is true, then we would be able to square this. Right? Can we do the same thing here? Well, I don't know what the square root of a matrix really means, but we can think about this relationship, the relationship we had that for a to the k, it's x lambda to the k equals multiplied by x inverse. And remember that the square root of, this should be b equals the plus or minus the square root of a. And remember that what do we mean by the square root of a? We can also write this as the half power of a. So let's just think about plugging that into this expression. Let a equals q times lambda to the half q transpose. If this could work, then by the same rule, we should have b squared as q lambda times q transpose, which is a. And what would this look like? Well, we know that diagonal matrices are easy to work with. When we take the power of a diagonal matrix, we just take the powers of the diagonal elements. So let's think about taking this lambda, sorry, I keep writing a lambda as an a, which is not what it should be. We can think about constructing our matrix lambda to the half as the matrix where we take each element and take its square root. We have all positive numbers here, so this is a fine thing for us to do. Square root of 4 is 2, square root of 4 is 2, square root of 2 is the square root of 2. And so if we've constructed this matrix, then let's just plug that into this product of q lambda half q transpose, and again multiply through. Scale the rows of this first matrix. I'm taking the first product of the rightmost two matrices, gives us 0 2, 0. 2 over root 2 is just root 2, so this second row gives us root 2, 0, root 2. And root 2 over root 2, of course, is 1. And so this third row scaling gives us -1, 0, -1. We then take the second matrix product, again multiplying the first row by the first column, 0 plus root 2 over 2, root 2 over root 2, which is 1, minus negative 1 over time root 2 times -1, so this is plus 1 over root 2, as we have here. Second column, 0 plus 0 plus 0. Third column, 0 plus 1 minus 1 over root 2. Second row, 0 plus 0 plus 0. 2 plus 0 plus 0 gives us a 2 here. And 0 plus 0 plus 0 gives us a 0 here. Similar to the last example, we just have a difference in sign here that gives us 1 minus 1 over root 2, 0, and 1 plus 1 over root 2. This matrix satisfies our general rule. You could double check that this all works out. I've gone through this process of actually working through the math with this special matrix lambda to the half. We actually could have found this directly using the form that we had found here and plugging in k equals a half. If we had done that, what would we get? If we wrote k equals a half, what is 4 to the half? Square root of 4 is 2. 2 over 2 is 1. Plus square root of 2 over 2. Square root of 2 over 2 is the same as 1 over square root of 2. That gives us the same expression here. 0, 1 minus square root of 2 over 2. 0, 4 to the half is 2. 0, 1 minus square root of 2 over 2. And 0, 1 plus square root over 2 here. This gives us exactly the same matrix. This actually raises an interesting idea about powers of matrices. At least when we have positive eigenvalues, so square roots of those terms are allowed, we can define something that is not only integers and positive integer powers of a matrix, but we can also define fractional powers of a matrix, something equivalent to square roots, cube roots, and so on of matrices. These have applications in some more advanced applications that we are not going to get into in the context of this class. With that, we've gone through some examples. How do we see when a matrix does not have an eigenvalue decomposition? How do we find the special case, so-called spectral decomposition for a symmetric matrix? And how do we use an eigenvalue decomposition to simplify the evaluation of powers of matrices, even in the case where we can have fractional powers? That wraps up our worked examples for the Unit 10 on the eigenvalue decomposition. Thank you and goodbye.